A black hole can evaporate, yet keep every secret intact. The immediate takeaway is simple. Physics says information never truly disappears. Not in stars, not in atoms, not even in horizons. It only hides, spreads, and scrambles into strange places. That claim sounds bold because entropy screams that order decays. But order is different from information, which tracks microscopic details precisely. This is the universe's weird promise. Evolution is reversible underneath. Burn a book and the ash still encodes it. Hopelessly scrambled, yes, but not annihilated, if you could reverse everything. That idea unlocks black holes, time's arrow, and cosmic memory, and it shows why the universe never actually forgets. Stand beside a black hole's edge, watching light bend like taffy. Information means the exact microstate, the full list of physical details. If information vanished, physics would lose predictability and fairness. Quantum theory avoids that failure, with dynamics that are reversible. Unitary evolution is a fancy term for perfect rewinding. Every possible past maps to only one unique present. And every present maps to only one unique future. Nothing gets deleted, it just moves and spreads through entanglement. Tiny test, imagine shuffling a deck with perfect gloves. You can unshuffle by exactly reversing each precise move. Same with molecules in a room, drifting and colliding. Reverse every velocity and the gas reassembles its pattern. It looks impossible because errors explode as time grows. But the rule underneath stays clean, no microscopic facts vanish. We notice decay because we ignore overwhelming microscopic detail. Entropy measures that ignoring, counting how many microstates fit. High entropy means many microstates match the same blurry picture. Low entropy means only a few match that picture. So information is not destroyed by entropy, just hidden. Mechanics here is simple. The map is a reversible permutation. Quantum mechanics refines that, using phases that never truly disappear. Those phases carry interference patterns, like overlapping ripples on water. Lose track of them and predictions look fuzzy and thermal. Track all of them and the movie rewinds perfectly. Concrete number, a mole contains about 10 to the 23 particles. Their state defines a ridiculous amount of detail, beyond imagination. We compress that into temperature and pressure, then call it done. The universe keeps the rest, tucked into phases and correlations. Bottom line, unitarity means the cosmos preserves detail underneath change. Open a cryogenic lab door, white vapor curls across polished steel. Here is the link between information and heat. Erasing makes warmth. That's Landauer's principle. Deleting one bit dumps kT ln2. It matters for the universe because memory has energetic costs. When you lose track, you push entropy into the environment. Mechanically, logic gates can be reversible or irreversible operations. Reversible gates like the Toffoli never erase and never heat. Irreversible gates like erase compress many possibilities into one. That compression must expel heat somewhere to keep books balanced. Maxwell's demon once seemed to cheat entropy by sorting molecules. The catch is bookkeeping. The demon's memory must be reset. Resetting that memory costs energy, restoring the second law. Example in real terms, hard drives warm when you delete. Cooling a quantum computer is difficult because errors produce heat. Erasing a petabyte at room temperature releases measurable joules. Not much alone, but vast at data center scales. Translate that to nature, every forgotten detail warms its surroundings, and every stored correlation must be maintained with careful work. Quantum measurements spread information outward into pointers and photons. Those environmental records make outcomes look classical and durable. You can sample those records without disturbing the central system. That's why many observers agree on the same macroscopic facts. Numbers help. kT ln2 is tiny per single bit. At 300 Kelvin, it's around 3 times 10 to the minus 21 joules. But multiply by astronomical counts and the budget becomes significant. Net result, forgetting has a price, so nature pushes information outward. Watch a black hole glow faintly, like a coal in darkness. Stephen Hawking showed that horizons radiate using quantum field theory. That radiation looks thermal, carrying almost no obvious structure. If the whole evaporates completely, where did the details go? The paradox is sharp. Either information dies or quantum theory breaks. Stakes are huge here because both options feel unacceptable. The current picture says neither happens. The correlations hide subtly. Hawking pairs form near the horizon. One escapes as light. The partner falls inward, carrying mirrored quantum information. Over time, the outgoing radiation becomes highly entangled with itself. The curve describing that entropy is called the Page curve. Early on it rises, later it turns and falls. By the end, the emitted radiation holds complete information. Mechanically, the hole and radiation act like a scrambling circuit. Each emission mixes the interior records into the outgoing stream. Recovery looks impossible locally, but possible from the whole sky. Think of decoding a whisper using microphones placed everywhere. A concrete scale helps take a 10 solar mass hole. Its lifetime is about 10 to the power of 67 years. The glow is faint, colder than the cosmic microwave background. Small black holes evaporate faster, releasing information more quickly. Observables include subtle correlations between far-separated photons. Detecting them is beyond current instruments, but conceptually clear. Common mistake is assuming thermal means truly random forever. Thermal means you lack details, not that the details vanished. So the picture is, evaporation returns information in complicated form. Thread the cosmos with filaments of light, weaving a vast web. Holography says volumes are encoded on bounding surfaces with area. That principle matters because it limits information by surface size. The core idea appears in ADS and boundary conformal theories. Bulk gravity emerges from many simple degrees of freedom at edges. Entanglement ties regions together, stitching geometry like a quilt. Increase boundary entanglement and bulk connections become stronger bridges. Decrease it and bridges pinch off into separations. Ryu-Takayanagi gave a geometric rule for entanglement entropy. You draw a minimal surface, then measure its area carefully. That area predicts the entropy of the boundary region. Example that anchors the idea, black hole entropy scales with area. 1/4 of the horizon area measured in Planck units. That number counts microstates, the hidden ways matter can arrange. Quantum fields dancing on the boundary encode the interior dynamics. A message thrown into the bulk lives on the rim. Recovering it uses the right boundary subregion, not every point. That is called entanglement wedge reconstruction, a coded retrieval. Quick mental image, a shattered mirror still reflects a face. Enough pieces recover the portrait, even if some shards are missing. So the picture is, surfaces set the budget for bulk information. Walk through a hall of cracked mirrors, shards floating like leaves. Error correction is the trick that puts faces back together. In physics language, spacetime behaves like a robust quantum code. That connection matters because codes resist noise while keeping content. The operation feels different from simple storage. It is active redundancy. Multiple physical pieces represent one logical piece of data. Lose a piece or two and the logic remains intact. The ADS bulk works similarly. Interior facts are redundantly stored. Many boundary regions can reconstruct the same interior qubit. That redundancy makes geometry stable against local damage or erasure. In practice, think of the 3-quadrit code that corrects erasure. Logical states are distributed across 9 physical levels coherently. Remove one whole quadrit and the logical state survives. More sophisticated codes handle more errors using clever entanglement structure. Rule of thumb, redundancy protects information, even while parts drift. Numbers give weight, a code distance sets tolerated error counts. Increase the distance, and the logical content becomes safer. Experimental quantum processors already use surface codes for stability. Those codes spread 1 qubit across many entangled neighbors. Lose a few, and error syndromes guide clean recovery. Translation to spacetime is poetic but technically serious research. Patterns of entanglement map to distances and even curvature. Example in clarity, toy models rebuild bulk operators from boundary sets. Net result, the universe seems to favor codes over fragile storage. Dust floats in a sunbeam, each grain flashing like a beacon. Records form when systems imprint on their vast environments. That process is called decoherence. Phases leak into many channels. It matters because redundancy creates stable, shareable classical facts. Here is how it plays out. Scattered photons pick up imprints. Air molecules carry traces, as do vibrations in solids. Those imprints are copied many times, becoming robust observational evidence. Anyone can read them, without disturbing the original object. Quantum Darwinism describes how many copies make consensus reality. The environment acts like a public ledger of macroscopic events. Example set, tree rings archive rainfall patterns across many seasons. Glacier layers track ancient dust, temperature, and volcanic eruptions. Seafloor sediments store microfossils, revealing ocean chemistry through ages. Cosmic records exist too, like the microwave background photons. Their last scattering snapshot preserves conditions about 380,000 years post-Big Bang. Gravitational waves carry memory, tiny permanent displacements after bursts. Numbers again help. CMB anisotropies are parts in 100,000. Those ripples map sound waves in plasma, like fossil music. Modern telescopes read those patterns, extracting precise cosmological parameters. Common mistake is thinking measurement creates information from nowhere. Measurement redirects and copies information into accessible forms. So the takeaway is, the universe writes and rereads durable records. Stand at the edge of time, watching galaxies drift beyond reach. Accelerated expansion stretches space, leaving islands separated by horizons. De Sitter space carries entropy, proportional to the horizon area. That number caps how much information fits within one patch. It matters because cosmic observers have limited access to records. In effect, horizons act like one-way curtains for signals. Gibbons and Hawking showed such horizons have a faint temperature. They radiate weakly, like a black hole would radiate. Information then distributes on the horizon, in principle retrievable. But retrieving it requires absurdly long times and precision. Meanwhile, local structures thermalize and decay, while heat drifts outward. The gravitational memory effect leaves permanent coordinate shifts after waves. Those shifts store tiny bits of passing event history. Example with scale, our observable patch contains about 2 trillion galaxies. Over trillions of years, many will recede beyond our view. Their light redshifts into radio whispers, then fades into background. Any memory we keep must ride resilient carriers like neutrinos, or live encoded across horizons as ultra-global correlations. Numbers again, de Sitter entropy is area over 4 Planck units. With today's horizon, that is about 10 to the power of 122. That astronomical bound sets a ceiling on stored cosmic detail. Bottom line, expansion limits access, but does not delete fundamental information. Hold a glass vial up to starlight, as if bottling a secret. The story began with a bold claim about black holes. We saw that physics preserves detail, while entropy hides it. Scrambling is not deleting, it is disguising under countless correlations. Holography adds a twist. Surfaces can budget and protect content. Error correction shows how redundancy stitches space into something stable. And records spread everywhere, from tree rings to ancient photons. So the universe keeps faith with information, even across ages. Calm thought, it never forgets, it just makes recovery demanding. If this expanded your cosmic intuition, follow for future deep dives.